Hi, and welcome back to the Save It for Parts channel, where I clearly have a globe problem. Now, these are not just a collection. I am actually trying to build a model for OpenSauce 2024 that represents geostationary orbits. Now, I've talked about different satellite orbits in the past using a little model of the USS Reliant from Star Trek, and we talked about the difference between low Earth orbits and geostationary orbits. For the OpenSauce convention, I wanted to do something a little bit more interactive and more to scale. So to represent geostationary orbit at scale, I've 3D printed a whole bunch of little miniature satellites. Obviously these are not to scale with the globes because that would be a huge satellite, but I want to show the actual distance, the scale distance away from Earth's surface. A low Earth orbit satellite, like we showed before, is just a few hundred miles up, relatively close to the Earth's surface. So a polar orbiting weather satellite, like say NOAA 18, is going to be going over north to south around the Earth as the Earth rotates underneath it, so it's going to be seeing a slightly different track on each successive orbit. Things like the International Space Station are in an inclined orbit that pass over both Florida and launch sites in Russia so that both the US and Russia can send up resupply missions. GPS satellites are out in a medium Earth orbit, and all these satellites are going at different speeds. So a low Earth orbit is around 17,000 miles an hour. A geostationary orbit is not only really far away from the Earth, but it's going a lot slower, about 7,000 miles an hour. So basically the speed and orbital properties of that satellite in geostationary orbit mean that it goes around the Earth once every 24 hours. But the Earth is also rotating once every 24 hours, so the satellite in geostationary orbit essentially stays locked relative to one position on the Earth. So for an observer on the surface, that satellite always looks like it's in the same place. That's why most of your TV dishes don't move. They just stay fixed on one satellite at all times. Now, when it comes to what does 22,000 miles look like to scale, we have to consider the Earth is only about 8,000 miles in diameter. I'm using very rough rounded numbers here. So if the Earth is about 8,000 miles in diameter, 22,000 miles way over there. So we can't really use the big globe here and have a manageable size of display. And it turns out on even a relatively small 6-inch diameter globe like this, geostationary orbit is going to be almost 17 inches away. So my little satellites would have to be way out from this thing, and that would be, again, a pretty unwieldy display to have on a table at a conference. So I've tried getting a few smaller globes. I ordered a couple of these from Amazon and they came in like a 4-pack. I wanted to go with this size, but I don't really like the artwork on these. They're just too derpy. They're not very detailed. I don't know, they're kind of junk. They're not for educational use, as they say on the package. They're for novelty and decoration only. So we're kind of left with this little baby globe. This one is about 3¼ inches. The rest of these, I don't even know what I'm going to do with them. Maybe we can find some other project for all these in the future, or hang them up in the garage and make for a really weird multiverse planetary system. So for the little 3¼ inch globe, geostationary orbit to scale is just over 9 inches off the surface. Still pretty big, but that's the best we're gonna do without going with like a marble or something. I have some thin metal rods that I need to figure out how to put in or through the globe here. I'd like this to still be able to rotate. I'd like to be able to show that as the Earth rotates, the satellite stays in the same position over the Earth. Now, little globes like this that are tilted on their mount do attempt to show the axial tilt of the Earth. That's what gives us seasons, but they're not super convenient to have something on there spinning around way off of axis, way out in the middle of nowhere. So I'm gonna go with the straight mount like this. I'm just gonna try to disassemble this a little bit and steal the mount from it. Fortunately, these are basically all on the same threaded rod system. I think this thing is just cardboard, so I'm trying to poke holes in it with a push pin. See if we can get our metal rod all the way through it. I actually have to take this off the mount and shine a light through it so I can see where my metal is going, and then we'll have to bend it later on to go around the axis here. Got it through. Okay, we got our second one through. That actually took about half an hour of fiddling to try to get them across because they run into each other in the center. All right, so here is our geostationary orbit to scale. Again, distance scale, not size. This is still pretty unwieldy for a conference display. This might take up quite a bit of the table, but you know what? I think it'll work. I think we can make it work. My next question is just, how do I get this out to San Francisco and assemble it out there? This took a lot more time to assemble than I expected, to actually get these wires through here, get everything lined up correctly. This might be what takes me the longest time to actually set up. People are going to be handling it, and I expect these are going to pop off, they're going to disappear, they're going to get broken. So again, I have a few extras, and I might end up 3D printing some more additional ones. And yes, it would be fun to fill out these orbital slots a little bit more, have even more satellites circling the globe, but I think that would be a lot more work. So we might just stick with 4 here for now. So how does this relate to my open source display of the miniature radio telescope? I'll throw an overlay up here that shows what my miniature radio telescope sees when it looks at geostationary orbit. It's basically an arc or an arch of satellite signals. These are all television satellites beaming down towards Earth. So if these are all around the equator in the same line, why does it look curved from the radio perspective? We're standing here in the northern hemisphere, again, not to scale, and our human or satellite dish is essentially looking down towards the equator. So anything orbiting above the equator is going to look higher in the sky from our guy standing here on the Earth. For the southern hemisphere, it would be basically the same. We're just looking down towards Earth north. And again, our satellites are going to appear up in the sky to us. Now, since our observer is looking downwards towards the Earth, satellites directly ahead at the same longitude are going to appear highest overhead. If our observer is off to the side from the satellite a little bit, then the satellite will look like it's off to the left or the right for this one, and it's going to look lower on the horizon because he is looking, again, straight ahead, but his line of observation is going to appear lower for stuff off to the far left and off to the far right. We can look at this another way. We can go to some astronomy websites and we can pull up what do geostationary satellites look like from a given location in the northern hemisphere. If you think of these satellites as a ring around the Earth, we standing in the northern hemisphere are looking down on the ring at an angle, so we see it as a curve. Now, if our observer stood on the equator, the satellites would appear in a straight line, but they'd be directly overhead. He would have to look straight up in the sky to see satellites in geostationary orbit because they're directly over the equator. And this is why satellite dishes are pointed in different directions on the equator versus far northern or far southern latitudes. When I used to play the old GeoGuessr online, I often used that as a hint to where in the world I was looking by just looking for satellite dishes on nearby houses. And yes, I'm going to bring some of these little guys out to open source as well. Alright, so does this make sense from a scientific standpoint? Maybe. I'm not great as a teacher or an educator, but I do like making little models, and hopefully this is going to help some people see how some of these things work, how these orbits work, and why they look the way they do from the surface of the Earth. If you're at Open Sauce 2024 in San Francisco, you might be able to come and play with this at the Save It for Parts Miniature Radio Telescope booth. Thanks for watching, and we'll see you next time.